Hello, good afternoon. We continue with the short course. This is the fourth lecture in the series on the finite volume method. So let's look at the linear solvers. CFD involves discretizing a domain of interest into elements called finite volumes. This converts the partial differential equation into linear algebraic equations for each control volume. If there are non-linearities in the equations, then a discretization scheme is used in such a manner that it will linearize the system of algebraic equations. This can be very important. The linear algebraic equations for all finite volumes form a square matrix. It's an n by n matrix. So this matrix, Ax equal to B, is solved for the unknown x by a linear solver. There are two classes of solvers, direct solvers and iterative solvers. Let's look at them. Direct solvers are the one that give you the solution in one step. Okay, you put all your coefficients into the matrix and out comes the vector x. It basically involves computing the inverse or the determinant of the matrix or some kind of a triangular factorization. Most popular of these, or most common of these, is the Gaussian elimination or the LU decomposition. The only thing is it requires on the order of n cube operations. So the matrix is n by n, it'll be n cube operations. Algorithms have been devised, especially for sparse matrices, which CFD produces, where this can be reduced to the power of 2.37, just under 2.5. Nonetheless, as we'll see, it's still pretty time-consuming. A very efficient and fast method is that of tri-diagonal algorithm, or the cyclic reduction, often called the Thomas algorithm. But the only thing with tri-diagonal is it can only use for a system where we assume there are only three connecting lights, like a 1D system has one node connected to nodes. That's a tri-diagonal system. One way to use it for multidimensional flow is to take each line or some string of elements which are connected together and then assume, take one, two around it, three rows like that, and assume they're connected and everything else is known. Okay, so we'll go in one direction at a time, so to speak, right? We can select the X direction row, then the Y direction rows, then Z direction rows one by one. That is very useful. The last of the direct solvers that I'm going to talk about is the Cramer's rule. It's very simple. It's basically simple substitution, but it's very time consuming. It's on the order of n plus 1 factorials. So you can compute what that is for a small n, but there are some attempts to develop n cube methods for this one, but it's seldom used in real large problems. The main disadvantage of direct solvers are that they're very time consuming, often prohibitively so. The CFD grids with a million nodes are very routine today, right? So if we take that, the number of operations is on the order of 10 to the 18, right? The Intel 9.5 i9, which is a fast chip by today's standards, it's in the teraflop range. That means it can do 10 to the 12 floating point operations in a second. On this fast system, it will take 10 days to solve this matrix. Okay. Now, the problem is that we don't usually solve the matrix only one. It's a time-dependent problem. It requires large number of time steps. 1,000 steps is perhaps the minimum. You may need to take 1,000,000 steps. Now, if you're doing a steady state solution, you use a steady state method, there's no time step, but the process is very similar. Now, instead of time steps, you have iterative steps, and they can be in the same range. 1,000 is not uncommon. The second problem is that the nonlinear problems require iterations within a time step because of linearizing, right? So there is another factor. You may need steps which are the linearized steps to take account of that, and then you may need iterations on top of that for the from step to step iteration. So The other thing is that parallelizing a direct solver is a challenge. It seldom scales up with the number of cores. Actually, the number of cores that are efficient drops off very fast with a parallel solver. This is because the bandwidth it depends on the bandwidth. So now even supercomputers or multiple computers for such a system would have hard time when you say you have to do 1,000 steps and you have to do 10 to the 18 operation or somewhere thereabouts. And on top of that, you may have multiple equations to solve. For example, a simplest Navier-Stokes equation would have 4 equations to solve. Okay, so all this puts direct matrix solvers almost out of the reach, except for a limited class of problems. Now let's take the iterative solvers. Iterative methods are the method of choice for most practical problems. What it involves, you make a guess and you say, this is the solution, but then you find this is not the solution, so you prove that solution at each iteration. It's less expensive, but it's more easily parallelizable also. Often the order of operations required is n log n. That's, of course, the ideal. You may have, 10 times that, but I'm saying that a good iterative solver can approach that. So for the similar 1 million nodes, the operations would be on the order of 10 to the 7 rather than 10 to the 18. Now that means the I9 will give you a solution in a fraction of a second, okay? 11 orders of magnitude different. The primary drawback of iterative solvers is, of course, that there could be poor convergence or even no convergence, and the solution never reaches a final value. Okay, it can also oscillate. It can also grow and grow up and blow up. But good iterative methods should converge rapidly. And what it depends upon is how the matrix is, what the matrix is composed of. It depends on its eigenvalues. Usually good convergence is approached if the largest eigenvector is less than unity once properly normalized. So one of the ways to get it to that is to suitably precondition the matrix, and that improves the convergence. So what's preconditioning? Preconditioning basically reduces the condition number of the matrix. You do it by either multiplying it by some vector or another matrix, so there are many different procedures. So condition number of the matrix basically shows how sensitive the solution is to small changes in value. Take a case where some coefficient or something else like a heat transfer may depend, a radiation may depend on T to the 4. So a small change in T will create a big change in the result. So similarly, if your stiffness vector is such that there are these highly sensitive implications, then of course you will have a problem with it, and a preconditioner can reduce that condition number. So suitable preconditioner is perhaps most crucial for convergence. One, if your matrix is not already has a good eigenvalues, you must use a preconditioner. So what are the linear solvers? Well, the classical one is the point-wise method called Gauss-Jacobi. Okay, the two mathematicians who developed that. It basically says that you have some values, initial values, and you solve for the next point, and all the other values you use at the previous time step. Let's say it's a time step situation or iteration in the same way. You come to point number 1, then let's say it's connected to 2, 3, 4, 5. 2, 3, 4, 5, you use the old values, and at 1, you compute the new value from these. So it's an explicit system, okay? So you repeat it till you get convergence. The Gauss-Seidel was a big improvement on that. So here what Gauss-Seidel did was that he took the Gauss-Jacobi method and he said, let's use the latest values. Let's say we computed 1 already, and now we need to compute point 2, which is connected to point 1. Well, we already know that 1. So we don't know 3 and 4. So what we'll do is use the 3 and 4 values, the old values, and use the 1, which is the just computed value. So you use the latest values. That is simple, popular, and usually it improves convergence quite a bit. Of course, convergence does require diagonal dominance, as I've said before, but it's usually satisfied for the CFD systems, properly posed problems. Now, then the next method, which is very popular, is basically successive over relaxation. So successive over relaxation is applied on top of either Gauss-Seidel or Jacobi or any other method. It could be applied even with a direct solver, you're iterating on that. What it says is that if X is your computed value and X old is the old value, then weight the two, and that becomes your accepted value for next step, right? So let's say you're step number 2, you have values at step number 1, you have values at step number 2, you just computed it, but now you replace the step 2 value with a new value, which is theta times the new value plus 1 minus theta times X. So if theta is 1, of course you use the new value. If theta is 2, you've given more prominence to the new value and less added or subtracted from that the old value. Now, what that does is essentially you're introducing a gradient-based system where you're saying, I know the gradient of development of the solution, and I'm going to overestimate where the gradient should go. Then these two steps are saying, but that's where it's going to go, right? It's like saying the weather for the last 2 days was good, so the weather next day is going to be good. Now, there is other situation with the non-linearities. And so instead of over-relaxing, we under-relax the system. So under-relaxation means that theta is less than 1, right? And that comes very handy for non-linear system, the other system which may not converge very fast. Now, the other classical method is line-by-line method such as ADI. I call it iterative, but actually you solve each line, like I said, with a tri-diagonal matrix. Like I said, the Thomas algorithm is used for that. So it is exact for those 3 at that time with the values, but it's actually iterative because you are doing it line by line and you don't know the values at all the other adjoining lines. So this is called the ADI method, alternating direction implicit method. So this usually is considered much better than the Gauss-Seidel, and it actually is very good if you can do it in the direction of flow. Usually your solution converges very fast. There is a whole new class of problems called Krylov problems, Krylov subspace methods. Now, what are these? They basically say start with a guess and compute the residual from that guess. Now, compute a correction to the previous solution in terms of powers of the matrix multiplied by the residual, right? What it is essentially doing, like we did with SOR, is it's basically saying, look at what the gradient is, right? The residual gives you an idea of where the gradient is going to go. And it's basically saying that based upon that, I'm going to say the next value will be there, okay? So these methods are very ideal for large sparse matrices, and they can be specialized for symmetric or non-symmetric matrices. So perhaps 2 of the best examples are the conjugate gradient and the GIMRES. The conjugate gradient is used for symmetrical matrices such as pressure, equation, heat, and conduction, and it's kind of called biconjugate gradients variant. Is basically big G, big stab G is basically can be applied to non-symmetric matrices. GIMRES basically is an interesting method. In theory, it should produce the solution if one exists. Okay. What it does is it stores a number of previous resolutions, right? So it's an even better guess on where the solution is going to go. It's not unknown to have like 30 solutions stored. Okay, it's very expensive in a storage, but if you store enough solutions, then you can say, I know where I'm going, right? So this is a very, very good method from that point of view. So again, like I said before, preconditioners are almost a must with all these methods. And it is a very active area of research. Now, very important point you have to keep in mind is what is called the round of errors. What are round of errors? These are caused by the fact that today's computers store decimal numbers with a limited number of bits, right? Single precision has 32 bits, which can store about 7 significant digits only. 64-bit increases to 16 digits. And 128 quad precision can have as many as 37 significant digits, right? The problem is when you multiply, let's say 3-digit numbers, the result is a 6-digit number. 4 by 4 is 8. 6 by 6 is 36. Now, real numbers, quite often, they have many significant digits. Pi, for example, has how many? Endless significant digits, right? Of course, they're not all significant, but if you keep on multiplying, then there is a problem. So what happens is quite often there are registers, special register of multiplication, which are longer than the regular one, like a 64-bit precision may use a 128-bit register for that reason, right? But nonetheless, after doing that computation, they still have to store it. So I have to truncate it to the most significant digit in 16 digits in this case. The difference between the actual product and the actual addition and the one that is stored is the round of error. So round of error generally grows with the number of operations, and it can be enough to overwhelm the solutions. For example, it's been known for certain solutions where a laminar flow would begin to produce turbulence because of these random errors that occur due to round off in the flow. Okay. All matrix solvers suffer from round of errors. Even non-matrix solver, any operation you do has a round of error if your number is not an exact number in 16 digits. Usually the direct solvers are more prone to this because all the operations are done in one step and they're done continuously, so there's a more round off. Usual rule of thumb is that you get accuracy to only half the number of digits stored for large matrices. For example, if you're working with 64-bit double precision, 16 significant digits, you cannot trust the numbers beyond 8 if you can do that, right? So stop quoting your results to 16 digits with double precision, okay? Now let's look at a few issues that arrive when you use all these iterative or direct matrix solvers. So first is that after you solve the matrix, and this is direct or non-direct or iterative, the algebraic equation for that point is matrix is given here, right? So this is the diagonal component and this is the off-diagonal components. A B is the forcing function or the stiffness vector. So what has happened is the solution phi is computed, right? And the above quantity is satisfied. But computers, for a number of reasons, round off and other things, they may not compute the solution exactly. So there is a residue. So that residue is residue of that equation minus the diagonal component, right? So that's the residue of that equation, right? So the residue, the unscaled local residue, we can also compute a global sum of this over all elements. So that would be called the global residue. These are both unscaled at this stage. Now, quite often you normalize this residue and you normalize it with the diagonal component in this manner, right? So what you do with that one is that you have now gotten numbers which are comparable independent of what the values are in terms of the actual values, right? Another residue that commonly used to test convergence is the absolute difference of variable values between two iterates, k and k plus 1. You say that what is the difference between the 2 points? That's the residue. You can also use its normalized version, which basically says 1 minus 5p or 5k, right? Again, you can also compute the global residue or all the sum. So there are other ways of computing residues, such as the sum of disparities in fluxes or the change in the quantities for the whole domain. So all those are there. You should choose one that you think works best for your objectives, and that is very important. For most problems, we do not know the actual solution, right? If we knew that, we won't need CFD. So a residue only tells you how accurately the discretized equation has been solved. Right? You solve the AX, times something is equal to B vector, right? It is not a measure of error in the solution of differential equations, except in very limited circumstances. For example, you may have linearized the equation to prove it. For example, there may be time dependence in certain properties. There could be other reasons, your truncation, round off, all those are there, right? So you may seldom can say with confidence that this is the solution to the actual differential equation. It's not. So, but to test convergence, what we do, we choose a local or a global or a scaled or a unscaled of the discretized equations, okay? Or we can change the absolute range of values and all those things that we talked about. So solution is typically stopped when the residual has either fallen below a certain value, how will you define it, or it has reduced by a certain order of magnitude, typically about 10 to the minus 6, 10 to the 8, minus 8 is considered good enough for convergence. But it may also need to be stopped if there are oscillations that don't die, they keep on occurring for a long time, okay? There will be oscillations in the beginning, but if they stay on, then there is some problem. Similarly, there are situations where the residual continues to grow in an unbounded manner and would eventually a solution will blow up, right? So the first two indicate convergence, the second two indicate you should go back to the board. Okay, they indicate non-convergence or instability, look at what is going wrong and why, and come up with a better approach. So iterative convergence, I strongly feel an engineer and strongly recommend that you always examine after you solve the equations with whatever residue criteria, examine the mass balance, or if it's thermal system, then thermal energy. If it's a species transport, then species, whatever it is, examine the total mass imbalance in the system. If something is coming in, something is going out, something is inside, how much is missing. So compute the algebraic flux, the sum of all fluxes through all the cell phases. And this is the balance for that particular element, right? So then compute the algebraic sum of the mass balance of all the elements, right? And finally, you can normalize it, let's say with the total flow of the system or some other criteria that you have, the total heat in the system, whatever you want to do, right? That gives you a measure of confidence. So this can be very important, especially when you use a method such as finite element, which does not inherently conserve the local fluxes, okay? FEM only ensures that you have a global minima. It doesn't ensure that at some points the minima is not large, right? So it is also very important because you may not have the exact solution algebraic analog, right? So if so, then that could be because of non-linearities in the case. You may linearize the equation. You may have convergence of all the time dependence problem. So all these factors become important. So it's very important to see what the fluxes are doing. As an engineer, I like to look at that. So it's a pity that by default, many commercial code do not give you the balance of these conserved quantities, such as mass, heat, or species. We made sure that our answer software, which is written by engineers, not computer programmers, always gives you the overall flux balance for all the solved equations. Now let's look at the issue which is related to it, that is that of grid convergence. So iterative convergence only ensured that the convergence of the solution is given at a particular grid. Grid convergence is when the solution to the particular problem has been actually solved such that it satisfies the differential equations as far as we can tell, right? So to do that, what we do is we solve the equation for a number of grids of different resolutions, and that's what we need to do. This is called the grid convergence or grid refinement study. The standard approach to approaching such a grid independent solution is to solve the problem on at least 3 grids with different resolutions, okay? Usually it's recommended you use N2N and 4N cells or cut the grid size by half and half and half. But sometimes you may not be able to do that. So you can do N, 1.5N and 2.5N, whatever you like to do. And if you don't see that the solution to some measure has settled down, then there is no option but to go back and continue and do a 4th grid, a 5th grid, a 6th grid, right? Let's assume the error for a particular grid size is E, and the system you're using, the scheme you're using is accurate to the pth order of the grid size H, right? This is H to the P. This is a constant, and this means higher order terms, right? So now if that is the equation that governs the errors, then we can neglect higher order terms for the moment. and we can take the log of this equation. So we get log of E is log P and P log Y. So we can basically invert this equation now to get P out of this equation. We can get the order by inverting this equation, as we'll see, right? So how do we do that? Before I do that, I would want to say that the Taylor series analysis are often not a real indicator of order of grid converter. You may say, oh, I'm using a first order scheme. I know it's first order. I'm using a second order scheme, second order. No, that's not so. I can tell you almost, for example, Quick is supposedly a third order scheme. I can challenge you and guarantee you, you will not get the third order accuracy, except for those few problems for which it was developed and tested, right? So reasons could be non-linearities, they could be mixed discretization scheme using the convective and diffusive term, they could be higher order derivatives, they could be all kinds of things, right? So we go back to that option of doing 3 simulations. And in this case, let's say we do a constant ratio of grids. Okay, here we say, let's say it's a factor of 2. So we say H1, the grid size is reduced by half, reduced by a quarter, and we get this. Okay, now if we do that, the equation that I showed you before basically says that the 3 solutions at the same point, of course, same location, the 3 solutions are related by this, and that's the order. Log of these 2 solutions divided by the log of the ratio of the grid reduction. So this is a constant R, right? Could be 2, and this is something else. So that's how you determine the grid size. Now with this, I think I'm done with the matrix part. I'm going to move to the finite volume formulation, the actual one of the one. So I'll take as an example a very simple case of a time-dependent unsteady heat conduction, right? So basically, very simple equation: gradient of temperature with time, diffusivity, and dt, dx, and s, right? So I'm just going to need, it's a 1D solution. These are my 3 nodes, W, P, and E, and I want to derive the equation for that. Just for illustration purposes. Let's assume that we know the values of the previous time step, T0, TE0, TW0, right? Now value at the current step, which are unknown, are designated by 1, right? So the first step in obtaining a solution is that we integrate the equation, right? For the control volume over this time period T to T plus delta T, we integrate and we get this equation, right? Okay, now this we can do simply by saying that this is the old value, new value minus the old value, right? This side, this one integral is done exactly because we have d by dx there and a dx there. So by Gauss theorem, this drops out. So we're left with k dt dx. So k dt dx at the east phase and the west phase. That's all this is, okay? So here we have assumed that the time derivative that we did here is actually backward difference. You look at it, it's just one quantity. It's not an average of some kind, right? So we still need to compute the right-hand side of the matrix. So let's see what that is. So let's assume that the right-hand values, which we don't know, are a weighted function of the new and old values. Of course, if the function is smooth and the function has a definable gradient, then this is the required from the continuity point of view, right? So this value must fall between the old and the new value, this average value at that point, right? So this is at one point, right? It's 2 different times, 1 point, and we say take f time of the new value and 1, just like under relaxation, right? So we're guessing. So if we put this weighting function in there, we get f times the flux at the new time, 1 minus f time the flux at the old time, right? If I make f is equal to 0, then this drops out. I know all of these values. So we now have an explicit system because I know everything on the right-hand side. TP0 is known. I can just compute TP1 from a simple formula, right? If I make it 1, then this drops out and I'm left with this one, and everything is unknown except TP0. This is unknown, this is unknown, this is unknown, right? So this is called fully implicit. Now, one of the very popular techniques is what's called Crank-Nicolson. There we put half of each, f equal to half at the old step, half at the new step. It has many advantages, right? So we'll talk a little more about this in the next slide. So, okay, let's just go to this one. There are three options that we can discuss here. We can make f is equal to 0. It leads to an explicit scheme. We can solve it directly for TP1, right? So it's first order accurate, right? Because we had a backward one-sided difference. It's also only conditionally stable based on the Courant number. The Courant number to be less than unity for this to converge. Okay. Now, when it is equal to 1, then it leads to fully implicit scheme. And that means we need to solve a matrix. Also, one advantage of this implicit scheme is that it's unconditionally stable, right? You can use whatever Courant number you want. Okay, it may not be accurate, but it's stable. Now, when f is equal to half the Crank-Nicholson, it's an implicit scheme still. You still need to invert a matrix, but the main advantage is it's a second order accurate scheme and also unconditionally stable. It does have some drawback that certain times, based upon various factors, nonlinearities and other things, it can give you spurious oscillations, right? But it will not blow up. Now, I'm going to take a bit of a digression here because I'm short of time, and I would cover, I don't know, about 10 slides on this subject, but I'm just going to do one. And what happens is when your K is varying, let's say your conductivity is varying, right? And there are 2 points and you are asked to get the value at this point E. At the midpoint is where we want, not here and there. K is a function of space or could be even a function of time. So simplest way is to write K is equal to a linear function, a straight simple function of Fe, 1 minus Fe. We use this many times, right? So we take a half and average, right? So this is the algebraic arithmetic mean, right? So usually it works well if the flux is parallel to the direction of grade, right? If the flux is there are 2 elements and they're connecting the 2 elements, and then it works well, right? And they have similar values on both ends. It doesn't really work well, for example, when you have 2 elements next to each other. Let's say the element E has 0 conductivity. And this element has conductivity of 1, let's say, right? So we're going to compute a value of half here, and we compute a flux. But you know, if I put a complete insulator here, actually there's no heat transfer. Heat transfer is 0 here, okay? So arithmetic is going to say it's half, and it's going to compute a flux between the 2. Well, that is not physically correct in this situation, right? So that's when we use what is called a harmonic mean. It is best if the flux from one enters the flux from the other. And in that case, what we do is that we would take a harmonic mean. So when this is 0, this is 1, this will be 0, right? That's the harmonic mean says, right? So arithmetic mean works best when the flux is in this direction, right? Across, okay? The other direction, grid I should have said here, not parallel, but normal to the grid on the normal to the other direction. And this works best when the flux goes in this way. Sometimes a geometric mean is used, not typically in heat conduction, but it's used quite a bit, let's say in groundwater flow or many other situations like viscosity and all that. And it's used when within the element, there may be stochastic variation of the values, and we've taken some kind of average value. Then quite often it's better to take a geometric mean. When there is a flow, again, in heat transfer otherwise, there are situations where you may want to take the upwind, and that can be relevant in many situations when the flow becomes very dominant. The conductivity also would be taken in that direction. So all these options are appropriate depending on the variation of K. We don't have time to discuss it, but we can arrive at any this problem can arrive with any diffusion coefficient, not just conductivity, and actually with many other properties. So let's now move to a 1D steady convection diffusion equation, the next on my list. So this is the equation now, right? So this is the module, the element, right? PE1, same. Now there are fluxes here, right? Okay. So let's consider this cell. Now what happened to this cell? This is the equation. We're integrating it over that control volume, right? if we do that with Gauss theorem, the discrete term becomes the convective flux here minus the convective flux here minus convective flux here, diffusive flux here minus diffusive flux here. So those are written here, convective flux at east, west, north, and then east, west, right? So if we define the diffusive flux D as gamma over delta X and F as rho times U, then this equation you can see simplifies to Fe times phi E, Fw times phi W, right? And this becomes dE times phi E minus phi P and dW phi E minus phi W, right? So one thing to note here is that I have used central differences in getting this discretized form, right? Okay. So this is what would happen with central differences. Now, in the derivation above, the interface E and W and the values taken average grid points are like that. D is like that, DE is that, F is, and phi E is taken as phi E plus phi P over 2. That's the same. That's what I meant by average second order difference, the central difference. And phi W is taken as that, right? Okay, but remember, we are in a convective diffusive situation, not a purely diffusive situation. So this may not be right. So before we proceed further, I want to point out that if we take the continuity equation for this case, the continuity equation can be integrated to give that d by dx, it's only one dimensional, is 0, which means this is 0, which means Fe is equal to Fw. This is 0. Now, you may think it's very simple 1D, but actually this happens even if a multidimensional problem, the equation is satisfied in a similar manner, there'll be just the other direction components here, right? So now the algebraic equation for the control volume that we wrote before, after putting the value of phi E and phi W, small a, small w by half, replacing them by half, what we get is we get the terms which look like that, right? D E W plus Fw over 2, dE minus F2 and all that, multiplied by phi P and all that. With just simple rearrangement, you can see that where I'm coming from in that, right? So because I did it this way, this term is there. Fe minus Fw arrives here. But we know that this is equal to 0, right? So we can simplify it one more and eliminate it. So this is the net equation that we're left with. Now let's simplify it for visual reasons. And we say, let's define Cw as this quantity, right? Ce as the convective term or the coefficient, sorry, these are influence coefficients, not convective coefficients. So the convective influence coefficient Cw is given by this thing. Ce is given by this one, right? And Cw is given as that, and Ce is given that, right? So this is what happens. Or if we normalize it in terms of Peclet numbers, this is what it means. It means the Cw is gamma over delta X, 1 plus Peclet over 2, and Ce is gamma over delta X, 1 minus Peclet over 2. Now, depending on the direction and speed of flow, you can see that Cw and Ce can become negative if Peclet number is greater than 2, right? Remember that equation, which was here, right? Okay, 1 minus Pe by 2. So Pe2 negative. So in this case, the matrix will not be positive definite, and we will not get a stable solution. That's because we had used central difference scheme for purposes of illustration. As we learned in the previous lecture, we must use an alternate scheme if Peclet number is greater than 2 to get a stable solution, because a non-positive definite matrix does not converge well. So upwind and hybrid schemes may be the first line of defense. I will leave it to you as an exercise to see what these influence coefficients become. If either of these is a different scheme is used, and see that the resulting matrix will stay positive. It not depends on the scheme you select. I'll also encourage you to select a scheme of your own and see what happens to the matrix. Can you devise one? Now, I'm going to come to the issue of false diffusion. False diffusion is the case when there is an extra diffusion added into the equation because of discretization, right? And it typically occurs when the flow does not exit an element at right angles to this element phase, okay? Well, actually, it's related to the grid lines and the flow to the grid lines, but that's usually what I'm saying here. So this means that diffusion is non-zero, even with physical diffusivity of 0. Or if there is a physical diffusivity, let's say your physical diffusivity is 1, false diffusion may add based on the Peclet number, a number like 0.1, 0.2, or maybe even more than 1. It can happen, okay? So this is caused due to truncation terms in the convection scheme, primarily. Okay, there are other terms that can add false diffusion, positive or negative, but the positive diffusion is typically added by the truncation of the first order term. This is seen very clearly in 2D and 3D simulations. Now, of course, we can mitigate it by the use of higher order schemes. Central differences can become unstable, though, if we use higher order differences due to spurious oscillations. Now, one thing to notice is that it's not just central differences, but all higher order schemes create instability or non-physical oscillations. There may be some exceptions, but that's what happens, okay? Actually, what is going on is that many higher order schemes, to get stability or depress physical oscillations, what they are saying is that a controlled artificial diffusion term is injected into the equation deliberately. You just control it, so it's smallest amount needed to stabilize it, okay? But what that does is it typically reduces, at those points where you did that, the scheme to a first order. So for a 2D problem where flow is aligned to the grid at an angle of theta, Duval Davis and Wolstein also, they derived equation that show that it's proportional to the velocity of the flow and the angle to the grid lines. So fault diffusion increases as the velocity increases, and it increases as the sine theta increases, right? So for example, it is at the angle of sine theta and large enough u, this can become actually larger than the actual Reynolds number you have. I mean, it can lower your Reynolds number because it will be larger than the actual viscosity you have in the system. So I know a problem, for example, I know of a square cavity where we solved it for a very large Reynolds number and it converged all right, but the solution was worse than that at a much, much lower Reynolds number. So this is one option. Now, just to illustrate this point, I'm going to take a very simple example. Here is a square domain. Flow is at 45 degrees, but lo and behold, it's constant. U is equal to V is equal to 1, so the flow angle is 45 degrees to this grid, right? Now, what we do is we take one variable, let's say temperature, and temperature is 0 on this wall and 1 on this wall. Now, what should happen in this case is that actually, if the diffusion is 0, then the solution should be like this. Okay, there should be a sharp interface between C0 and C1 once you increase the velocities, once the diffusion is 0. So diffusion coefficient is set to 0, but we still get this solution. This is a solution we desire with diffusion coefficient 0. What we actually get looks like that. Let's say we use a structured square mesh. Upwind will create this big diffusion front. Quick controls is better, but look at these oscillations, which are showing the instability, right? This is the instability that's created quite often by higher order schemes. If you do a bounded CD, then you get even a smaller diffusion, but again, you see that what it's showing, the unphysical representation of the fluctuations here, right? Now, look at unstructured grids, which are very common today. Now, the first thing you notice is there is very little difference between the three schemes. Bounded is not much better than quick, is not much better than upwind, right? So this should be very interesting, right? So this shows that how a third order scheme, which quick claims to be, reduces essentially to a first order scheme, right? So that's what happens. So simulation with central difference, of course, will diverge, right? So This is what happened with different schemes. Now, my last slide is a very interesting conundrum. I'm sorry, I didn't correct the number of total slides. We talked so far of how we need a higher order representation of the convection terms to get better results, right? That's the kind of the general wisdom. The fact is that when diffusivity is 0, the system of equations becomes hyperbolic, right? Supersonic flow is one example when the diffusion is negligible. Okay, I don't have the time to get into the definitions of elliptical, hyperbolic, and parabolic, but if you're interested, let me know and I can show you what that means. What essentially happens in a hyperbolic system is that the downstream values no longer affect the upstream value. So if flow in the Colorado is going from US to Mexico, the Mexican values of the concentration or temperature of the water do not affect the values in Denver, right? Rather, the upstream completely controls the downstream value. Actually, it's the temperature of Denver that will flow down to Mexico, right? So upwind scheme, you can see, is the best option here. And actually, under certain conditions, gives an exact solution to the equations. This is why the so-called method of characteristics is so useful and so popular for supersonic flow. It actually works. It's a very good method. It's basically an upwinding method. You say, look at the characteristics, where it's coming from, the influence is coming from that point, right? So the lesson is that first order scheme is bad only when the second order diffusion terms are significant. That's very ironic, isn't it? That first order scheme by itself is bad, diffusion is present, and now the first order becomes bad. It's like there's a bad guy, you are the good guy, and the bad guy goes away, you become good, and the good guy comes away, the bad guy comes close to you, and you become bad, right? Okay, so be on guard when you equate accuracy with order. Never do that, except for properties of, it's only for reasons of convergence that I find order is important, okay? What you two things you should trust is do your grid independent study, compute the order of accuracy if it's very time expensive to obtain solutions, right? And check the residuals of physical quantities like fluxes, the amount you have and how much you should have and where is the deficit in that. Those are the real tests in real life, not residuals, not discrete equations. You are an engineer. Physics, never forget the physics. Physics doesn't forget you, okay? As far as my professional life is concerned, for more than 50 years now, I've done nothing but CFD. And I can tell you there's never been a dull moment in my life. It's been so exciting. I've traveled from place to place, continent to continent. I've gone deep underground and I've gone to the, well, not literally to the outer reaches of space, though I've gone deep underground. But what I mean is that I worked on problems all the way from deep in Earth, like nuclear waste at, at 1 mile deep or something like that. And then I worked on designing things like space shuttles and rockets and things of that nature. On the other hand, and in between, all kind of problems. CFD is so varied today. I worked on the brains of mice, and I worked on, all kind of things. I don't want to bore you with those details, but it is a very interesting branch of science. It is fun. Thank you.